In 2021, NASA achieved a remarkable feat when the Parker Solar Probe fulfilled its mission to touch the Sun. While this description might seem hyperbolic, it accurately captures the essence of the probe's accomplishment, diving into the Sun's upper atmosphere, known as the corona. This mission represents a significant milestone in our exploration of our solar system's central star and pushes the boundaries of what we thought possible in space exploration. The corona, with temperatures exceeding 1 million degrees Celsius, presents an environment hundreds of times hotter than the highest melting point of any known metal. This extreme heat poses a formidable challenge to any human-made object venturing into its domain. Yet, against all odds, the Parker Solar Probe not only survived but continued to function and gather crucial data. This article delves into the fascinating physics and innovative technology that made this extraordinary mission possible. The challenge of extreme heat. To understand the magnitude of the Parker Solar Probe's achievement, we must first grasp the extreme conditions it faced. The Sun's corona, despite being farther from the Sun's surface than its cooler photosphere, reaches temperatures over 1 million degrees Celsius. This counterintuitive temperature gradient, known as the coronal heating problem, is itself a subject of ongoing scientific research. At these temperatures, conventional materials would instantly vaporize. Even the most heat-resistant alloys used in aerospace applications would be woefully inadequate. The challenge for NASA engineers was not just to create a probe that could withstand these temperatures but one that could continue to function and gather data in this extreme environment. Technological marvels, the heat shield. A significant part of the Parker Solar Probe's ability to survive the corona's heat comes from its advanced technology, particularly its heat shield. This shield, officially named the Thermal Protection System, TPS, is a marvel of materials science and engineering. The TPS is a composite structure about 11.43 centimeters, 4.5 inches thick, primarily composed of carbon-carbon composite material. This material is similar to that used in the nose cone of the Space Shuttle, known for its ability to withstand extreme temperatures during atmospheric re-entry. The outer layer of the heat shield faces the Sun and is coated with a white ceramic paint that reflects as much of the Sun's energy as possible. Behind this is a layer of carbon foam, a material that is incredibly lightweight yet highly effective at insulation. This foam is 97% air, allowing it to be both an excellent insulator and light enough for spacecraft use. The innermost layer of the shield is another carbon-carbon composite panel that provides structural support and further insulation. Between the foam core and this back panel are titanium water-filled tubes. As the spacecraft orbits the Sun, these tubes help distribute heat from the side facing the Sun to the shadowed side, where it can be radiated into space more effectively. This advanced heat shield allows the probe to maintain most of its body at around 30 degrees Celsius, comparable to a warm day on Earth, even while its sun-facing side experiences temperatures of about 1,377 degrees Celsius, 2,500 degrees Fahrenheit. The physics of survival, hot without heat. While the heat shield is crucial to the Parker Solar Probe's survival, it's not the whole story. The probe's ability to withstand the corona's extreme environment is also due to a fascinating quirk of physics: the difference between temperature and heat. In everyday language, we often use temperature and heat interchangeably, but in physics, they represent distinct concepts. Temperature is a measure of the average kinetic energy of particles in a substance. When we say something is hot, we mean its particles are moving very quickly. Heat, on the other hand, is the process of energy transfer between objects of different temperatures. This distinction is crucial to understanding how the Parker Solar Probe can survive in the corona. While the corona's temperature is incredibly high, its density is extremely low, about 10 trillion times less dense than Earth's atmosphere at sea level. This low density means that despite the high temperature, there are relatively few particles to transfer energy to the probe. To illustrate this concept, consider the difference between putting your hand in a hot oven versus touching a hot pan. The air in the oven and the pan may be at the same temperature, but you can briefly put your hand in the oven without injury, while touching the pan would immediately cause a burn. This is because the air, being less dense, has fewer particles to transfer energy to your skin compared to the dense metal of the pan. In the case of the Parker Solar Probe, the corona's particles are moving incredibly fast, high temperature, but there are so few of them, low density, that they don't transfer enough energy to heat the probe to dangerous levels during its brief passages through the corona. The mission profile. Timing is everything. The Parker Solar Probe's ability to survive in the corona is also due to careful mission planning. The probe doesn't stay in the corona continuously but instead makes rapid passes through it. During its first visit, the probe dipped into the corona for just a few hours. These brief encounters are made possible by the probe's highly elliptical orbit. It swings close to the Sun for short periods and then retreats to cooler regions of space. This orbit allows the probe to gather data from the corona while minimizing its exposure to the extreme heat. As the mission progresses, the probe's orbit will be adjusted to bring it even closer to the Sun's surface. Each pass will provide valuable data about the corona's properties, including its magnetic fields, plasma, and energetic particles. Scientific significance. The Parker Solar Probe's mission to touch the Sun is far more than just an impressive technological feat. It represents a significant leap forward in our understanding of our nearest star and the fundamental processes that drive space weather and affect life on Earth. By studying the corona up close, scientists hope to solve several long-standing mysteries about the Sun. The coronal heating problem. Why is the corona hundreds of times hotter than the Sun's surface? The probe's data may help explain this counterintuitive phenomenon. Solar wind acceleration. The probe is studying how the solar wind, a stream of charged particles emanating from the Sun, is accelerated to such high speeds. Solar energetic particles. These high-energy particles can pose risks to astronauts and satellites. Understanding their origins and behavior is crucial for space exploration and protecting our technological infrastructure. Magnetic field dynamics. The Sun's magnetic field plays a crucial role in solar activity. The probe's measurements will provide unprecedented insights into these magnetic processes. Future implications. The success of the Parker Solar Probe opens up new possibilities for solar exploration. The technologies and techniques developed for this mission could pave the way for even more ambitious projects in the future. One exciting prospect is the possibility of sending humans to study the Sun up close. While this remains a distant goal, the lessons learned from the Parker Solar Probe about surviving in extreme heat environments could be crucial for designing spacecraft capable of safely carrying human crews near the Sun. Moreover, the probe's success demonstrates that with the right combination of innovative technology and clever application of physical principles, we can explore environments once thought to be completely inaccessible to human-made objects. Conclusion. The Parker Solar Probe's mission to touch the Sun represents a triumph of human ingenuity, pushing the boundaries of what we thought possible in space exploration. By combining cutting-edge technology in the form of its advanced heat shield with a clever application of fundamental physical principles, NASA has achieved something truly remarkable. This mission not only showcases our ability to overcome extreme challenges but also promises to unlock some of the Sun's long-held secrets. As we continue to analyze the data from the Parker Solar Probe, we stand to gain unprecedented insights into the workings of our star, with implications ranging from improving our understanding of space weather to protecting our technological infrastructure and potentially paving the way for future solar exploration. The story of the Parker Solar Probe serves as an inspiring reminder of what we can achieve when we combine scientific understanding with technological innovation. It stands as a testament to human curiosity and our enduring drive to explore and understand the universe around us, even in the face of seemingly insurmountable obstacles. As we look to the future, the success of this mission invites us to wonder, what other impossible feats might we achieve? What other extreme environments might we one day explore? The Parker Solar Probe has shown us that with ingenuity, perseverance, and a deep understanding of the physical world, we can indeed reach for the stars, or in this case, touch the Sun itself.